All right, now that we've hit the 5-minute mark, let's go ahead and get started. Welcome everyone to the HyperX webinar for automating stress analysis and structural sizing. I am your host today. I'm Charli Cahill. My actual title for the company is Manager of Customer Development, but by trade, I'm actually an aerospace structural engineer. So today I will be running our software just like we see a real end user doing. Also, in the way of introductions, I'm going to jump to our website here. Just a quick introduction on who we are as a company. We were founded at NASA Langley in 1995, so we've been around for about 27 years now, and we are a commercial software company. Obviously, our flagship product is HyperX, and we also do engineering services where we have a team of skilled engineers that actually use our software on customer projects. And that's where I spent the first 3 years of my career in this company. I also want to quickly introduce HyperX. And in order to properly do that, we like to do that with this graphic here on our homepage on collieraerospace.com. So the whole point of HyperX is to center your design. And to us, what that means is minimizing your weight or bringing your weight down. We do that by allowing you a platform to find the lightest weight materials and dimensions, as well as exploring all of the different designs and cross sections that you might want. We move your schedule to the left. So we essentially allow you to attain positive margins within a shorter amount of time. And we allow you to seamlessly go back and forth from that analysis and that design type case. We also increase your producibility. So we give you a place to not only design for lightweight, but to design for producibility requirements as well. And then last but not least, we help you to get to certification right on time. So from the start, you're actually able to analyze and design with those typical aerospace analysis methods that you would need to certify your vehicle. And every step of the way, we give you that visibility in order to verify what you're doing. And then we'll also allow you to print all of that data in stress reports that you can use to supplement your certification reports. And putting all of those 4 arrows together, we get the X in HyperX. Now to introduce the problem at hand, I have another slide here. Oops, let me get to, there we go. So let's say in this case, I am the engineer in charge of design sizing this wing all the way up through PDR or preliminary design review. So this wing, we have a fairly coarse mesh, and it's a simple wing box model meant to represent something that you might see in the urban air mobility industry, as you're seeing in the graphics shown. A little bit of information on the model. I'm using a Nastran solver here, and there are 10 load cases applied, and I am going to implement an ultimate safety factor of 1.5 and an analysis temperature of 120 degrees. Now I'm going to put all of that information in HyperX and use our tool to optimize the wing skins, spars, and ribs to all of those external loads that are applied in my model. While I'm doing that, I'm going to be able to enforce all of those manufacturing constraints that I alluded to and be able to, as an engineer, understand the effect that those things have on my design results. Every step of the way, I'll be able to visually interrogate and verify my results firsthand. And then at the very end, I'll show you an example of a stress report that we can export in order to support something that you might need for a design review. So without further ado, I will go ahead and open up the software. And now what you should be seeing is the brand new HyperX interface. So the first thing you need to understand about HyperX is it is not a preprocessor. It's not a post-processor. It actually couples with your finite element analysis. So the first thing you need to do is you need to import a bulk data file. You need to import your FEM input file. This is where HyperX gets all of the element and grid definitions that it uses to understand the geometry. You'll notice, as I mentioned here, that I am using the MSC Nastran solver, but we're actually pretty solver agnostic. So if you use any of the other flavors of Nastran, NEI, NEX, or if you use Abacus, ANSYS, or Octastruct, all of those are supported. So I'll go ahead and import my model here, and you'll probably see that populate in the background. But before we start looking at that, let me toggle over to my FEA results tab. And just like HyperX uses the geometry from your FEM input file, it also requires the element by element forces coming from your FEA solve, so coming from your output file. These are the loads that it's actually going to be sizing to. And now from those two files, HyperX was able to determine that there are those 10 different subcases that were run in my FEM. So I have element by element loads for 10 different flight cases. And I've told HyperX which data to look for from those subcases. The last thing I need to do is I need to tell HyperX what to do with those element by element forces. And I do that by converting them into what is called a design load. So let me open up my design loads tab here. And you can see in this table that each row represents a design load. And there is one design load for each of the 10 subcases that I brought in from my FEM. So essentially what I want to do is I want to tell HyperX what analysis temperature and what safety factor I need to impart on these loads in order to properly size my structure. So I can do that for each load case. So I'll start with cruise. If I double click this guy, I can edit it. So maybe I'll say 120 and put in an ultimate factor of 1.5 and apply and close. And I can do that all the way down the line. Or you'll notice a theme here as we're working through this workflow. I actually have these buttons on the right that allow me to interact directly with Excel. So I'll push this blue button here, and you'll notice it exported a table that looks just like the one in HyperX, but now I'm able to copy this 120 and paste it. So all of my cases get that analysis temperature, and I'll do the same for my safety factor as well. Now I will save, close. Now all I have to do is hit this yellow button to re-import. And there we go. So now every single one of my subcases is going to be analyzed at a temperature of 120. So that's where I'm going to get my material properties for that case. And then I'm going to multiply my loads by a factor of 1.5. Okay. So now with all of that being said, we're ready to start viewing our model here. So obviously this guy that I'm rotating and spinning around in the viewport is our UAM wing model. Again, a pretty fairly coarse mesh. All of my element and geometry is coming from my input file. And the best way to interact with the model at this particular point, right after import, is through what is called our FEM tree, which is the panel all the way over on the left here. And if I expand this guy, you can see that the FEM tree is really just a summary or an echo of all of the data that HyperX found in your FEM. So you can see it's giving me a count of the number of elements per each type. It'll show me my property cards and things like that, my materials, everything that I might need. The other thing that I always like to point out is HyperX is actually able to identify and work with your element sets. So if I expand my EL here, you can see that my first element set, which is called assembly 1100 skin upper, if I click on this guy, all of the panels that correspond to my upper skin are selected. So the idea being that as an engineer, I spent a lot of time organizing my FEM in a way that's easy for me to work with. And in HyperX, I want to be able to utilize that or piggyback off of that when I'm doing any sort of setup or FEM work. So with all of that being said, the first thing that we need to do at this point is we need to tell HyperX what we want to size. We need to tell HyperX which of these FEM properties we want to carry over and commit to the database in order to actually run sizing operations on. So in order to do that, we're going to create what are called structures. So if I open up the structures tab of the ribbon and say create, there we go. And then I can actually use my element sets to make sure that I do this correctly. So if I want a structure that consists of just my upper skin properties, I will select that upper skin element set. And I will do that actually directly from my structures tree. So I'll right click and say create structure. And it'll actually populate with all of the elements from my selected properties. And it'll take the name from my element set. So we'll say create. And I'll close this guy. And now you can see after I've done that, in my structures tree, which is the second panel here, I'm now seeing a structure called skin upper, and all of my properties are now shown here. And if I look for these properties on my FEM tree, so if I go to this 2D list, you can see that the first few, the ones that correspond to my skin upper, have check marks, which also indicates to me that they've been moved over into a structure and that I should work with them there. So I'm going to do that with the rest of the model. So let me hide this upper skin so that we can more easily see. First, I'll make a structure for the lower skin. So I'll say right click, create structure again. And now I'll just put the rest of my internal substructure into its own structure. So I will highlight all of these guys in the viewport. Now right click and say create structure. Close my Outlook here. There we go. All right. So now that all of my properties have been committed to the database or have been committed to structures, I will close my FEM tree and I will effectively work in the HyperX world from here on out. So let me show these guys again. And now I'm ready to start defining my sizing. I've told HyperX what I want to work with. Now I want to tell it how I want to size these guys. So all of the information that will define that sizing or that analysis that I want to run is going to be held here in the property tree, which is located on the left right below the structures tree. You'll notice that there are several things already kind of pre-populated here, including my materials and a couple of different properties. This is because when I opened up this database, I implemented what is called a database template. So think about it like maybe my team and I got together and we decided on a standard set of materials, of failure criteria, and of design constraints that we always want to apply to this vehicle as a team. And all of these things have been incorporated into my database so that I and the rest of my team are using the same starting point when we're sizing. So the first step in implementing those things is to define the design space of our zones here, of our properties. So let me jump over to the design tab of the ribbon. The beauty or the benefit that HyperX gives you is that all we need to know is that these panels are 2-dimensional and these beams are 1-dimensional. They don't actually have a cross section yet. They don't have to maintain the cross section that we gave them in the FEM model, for example. So in HyperX, we can actually size and analyze these guys as anything we want. So for panels, we can analyze them as metal plates or solid laminates or maybe sandwich. We have several different options for stiffened panels if we'd like to do that. And then for beams, we have both open and closed type of design cross sections that we can use. For the sake of example, let's start with a solid laminate. Let's say we want all of our skins and all of our ribs and spars to be a solid laminate. So I will make a solid laminate design property. Maybe we'll call this solid laminate. Put it in zone-based sizing mode and rapid sizing. So there's 3 different sizing modes in HyperX. The first one that we're implementing here is rapid sizing, which is our non-parametric sizing routine. And essentially all the user has to do is supply a material for the given design variable, and HyperX will find the lightest weight solution that attains positive margin. And since we're using composites here, it's actually smart enough to take into account the various different things that we can implement in terms of producibility. So things like ply angle percentages, layup rules. So you can see we're enforcing symmetry here, for example, and fabrication rules. So I'm going to go ahead and give this guy a tape material. And now just to give you an idea of what kind of material data we take in, I'll double click this and show you here. So this is one of our basic materials. We obviously give it a name, a density, it has its own thickness associated with it. And just like with your FEA tools, we require you to input your stiffness values. Notice these guys are temperature dependent. And we also require allowables, things that we can write margins to. So for a composite, we recommend putting in stress and strain lamina level allowables, like the ones I'm showing here. But if you'd like, we also take in laminate level allowables that maybe you might get from test data or something like that. In the table shown here, we're looking at compression after impact strain data. Okay, so that's our design space. That's what we're sizing with. So I'll go ahead and apply this and save it to my database. And now if I go back to my property tree under Designs panel, I have my solid laminate design property. And what I need to do is I need to actually assign that property to the zones that I would like to inherit that design space. So I will use my structures tree to select all of the correct properties here. So I'll say 2D properties from the upper skin, 2D properties from the lower skin, and 2D properties from my internal substructure. And now I will drag and drop that property directly onto my wing. And you can see it turned green, letting me know that that assignment took. Now all of those zones are going to be sized as a solid laminate. I need to do the same for my beams. So I actually have a beam design property available. This came from my database template. So let's say my team and I have decided that when we're sizing one-dimensional beams, in this case, we always want to size them as caps. So in this scenario, we're implementing the second sizing routine. So rather than rapid sizing, we're using detailed sizing. This is our parametric sizing approach. So as the user, I had to actually input the minimum and maximum bounds as well as the step sizes for each one of my design variables. And HyperX is essentially going to check all of the different possibilities that live within this design space and find the lightest weight one that attains all positive margins of safety. So now I will again use my structures tree to select my beams, and I can drag and drop either directly onto the model like this, or I can even bring it up to the structures tree right here. And you can see again that green telling me that that selection took. The next step is for me to tell HyperX what to do with the element by element forces that are coming in from my FEA solve for each load. So I do that through what is called a load property. So back on my property tree here, I'll right click and I'll create a peak load property, which is our most popular load aggregation scheme. It essentially uses a series of metrics to flag the worst case load scenarios so that you don't have to size for every single force for every single element. And in this case, we're able to select which load components that we want included in that aggregation. So we'll say all of our shell loads and all of our beam loads are good here. And we'll click apply and we'll close. And now I will select my entire wing, all of my panels and beams, and I'll drag and drop that peak load property right there onto them. The last thing that I need to do is I need to prescribe failure criteria. I need to tell HyperX what I'm sizing against and what will constitute a passing design. So that is done through what are called analysis properties. And those are coming from my database template as well. So for example, if I open my solid laminate here, my team and I have decided, or maybe it's based on my company margin policy, that when we're sizing a solid laminate panel, we want to be sizing them against analytical panel buckling, ply-based composite strength, and laminate-based composite strength. And if I open one of these guys up, you'll see that these are actually categories. So within each category, there are several different methods that HyperX offers natively in order to size against. So many people in this group are probably familiar with what we're doing here in terms of ply-based. Max strain, max stress, Sci-Woo, Sci-Hill, all of the common ply-based metrics here. Okay, so I need to apply that that analysis property to my solid laminate panels. To do that, I will use, again, my structures tree to select my laminates. I will drag and drop directly onto my model. And similarly for the cap beams, similar story, I'm running stability, so local buckling and crippling of each beam, as well as sizing for ply-based and laminate-based strength. Again, I will select those guys and I will drag and drop. Now, if I'm ever worried about what I've assigned where or keeping track of which properties are assigned to each zone, you should note that the viewport is interactive with the tree. So if I were to click on one of these zones, you can see that this zone, when I have it selected, all of the properties that have been inherited by this zone become highlighted in the property tree. So I can see that this panel is a solid laminate, has a peak load property, and has been given my solid laminate analysis property. The idea here to give the engineer as much visibility and as much verification as possible before they hit that run button. Okay, so without further ado, it's time to go ahead and hit run. So I'm going to select all of my zones, and I'm going to use this play button over here to run my sizing. So again, remember, we're doing rapid sizing on the panels, and then we're doing detailed sizing on the beams, which is what it's chugging through right now. Notice that's taking a little bit longer just because it's chugging through all those different options. So now we are ready to start viewing some results. So I'll open up my legend here. And the first thing that we're plotting is a zone by zone plot of the minimum margin of safety. So the smallest margin of safety value that's essentially driving that design for each zone. We can also plot things like, for example, the controlling load case, or maybe the controlling criterion. I'll hide my upper skin so it's a little easier to see. And we can also plot our sizing results. So things like, for example, right now we're looking at the thickness of each one of those panels. Maybe since we're working with composites, we want to see that in terms of ply count as opposed to just thickness values. And we can see the dimensions of our beams here. So maybe I'll turn on the cap. Again, you probably noticed a theme here that the caps and the solid laminates are all kind of thickening up towards the root of the wing where we're seeing the most load. Another thing to point out here is I'm actually showing the weight in my structures tree. So back up here on the left, let me collapse these guys so it's easier to see. You can see that the weight is actually calculated per structure. And then we have a project total weight shown at the top that adds all of these guys together. So as you make your changes, as you do any sizing or analysis, you're able to directly see very, very quickly the impact of those changes on the weight of your structure. The other thing that I like to show in terms of results viewing is what we call our watch window. So everything that was plotted in the legend, oh, sorry about that. So everything that was plotted in the legend can also be tabulated in the watch window. So you'll notice if I expand here, the same menu that we're seeing. And it's actually dynamic. So if I select any of my zones, you can see that the watch window actually populates with all of the zones that I have selected, showing me the data that I asked for, which in this case was total thickness in terms of ply count, minimum margin of safety, and controlling criterion. And this table works a lot like Excel. So if I wanted to sort these guys based on minimum margin of safety, for example, I could do that. I can also Control A and copy and paste this directly into an Excel spreadsheet or maybe a Word report, anything that I might want to do to showcase this data or communicate it to my team. A special case, which is particularly useful in terms of interrogating data, and let me use the upper skin as an example here, is called our analysis watch window. So for the zone that I have selected, I'm seeing the margin of safety value written for every single criteria that was run on that zone. So you can see my analytical panel buckling as well as all of my strength criteria here. The first thing I'm noticing as an engineer is that my analytical panel buckling margin is pretty low, pretty close to zero. I'm pretty well optimized for buckling, but my next strength margin is pretty high. So I'm actually over designed in terms of strength. So that's leading me to have a pretty high weight here, actually in both of my skins. As an engineer, I might want to think about trying a different cross section for each of these skins that might save me a little bit of weight or maybe be a little more buckling efficient. So what I want to do is I actually want to change my skins to be a honeycomb sandwich design. So if I go to my property tree, I actually have a honeycomb sandwich design property already created. So you can see we're set up for rapid sizing. I'm using that same Collier thin ply tape for both my top and my bottom face sheets. And then I've implemented a Hexcel 4.5 PCF here for the core. And now I will show only my skins, and I will select and drag and drop that new design property directly on to those skins. And I will do the same with an updated analysis property that has more sandwich-based criteria, such as wrinkling, pore shear, things like that. And I'm already set up and quickly able to rerun those skins. Make sure you're paying attention to this weight up here. So now you can see I actually shaved off a little over 100 pounds in each of my skins just by switching to a honeycomb core cross section. And that's how quickly you're able to make design decisions and run trade studies here in HyperX. And I can actually view some of these results, verify that I have positive margins, all of those kinds of things as well, just to make sure. Another thing that we might want to implement at this point, maybe my dynamics group has come to me and said, hey, you know, we need to implement a certain EI requirement for such and such flutter constraint or such and such aeroelastic requirement. How do I implement that EI at a certain section of my wing? So in HyperX, we do that through what is called a section cut. So let me close my legend and kind of reorient myself here. And I'll go to my structures tree and create a cut. So I'll say draw cut, and maybe we'll go right in the middle of this third bay here. Now, when I click apply, you'll see that HyperX was actually able to draw the cross-sectional view of this cut that I just created. Now let me reorient my wing so you can better see that. So now at this section cut, the engineer is given all of the different section properties that you might need to know, especially when trying to communicate back and forth with your dynamics guys. So we give you your EIs and your GJs, all of your centers, all of that kind of stuff. We also plot it here too, so let me make it a little easier to see. You can see here, this little purple plus is your center of gravity, and then you also have your neutral axis and your shear center here. All of the properties and all of these locations that are shown, they're calculated, but they can also become constraints. They can also be optimized too. So in order to implement that constraint that I got from my dynamics group, what I would want to do is I would open up this constraints window and say, okay, they've given me a minimum EI, let's say of 9 e to the 8th. Okay. So that's my minimum stiffness that I want at this cut. What HyperX is going to do is it's going to apply that stiffness or apply a stiffness constraint to all of the zones that are part of this cut until that section requirement is met. And there are a couple different ways to do that. So at the far end of the spectrum, the lightest weight solution will likely be just to throw all of the stiffness in one component, throw all the stiffness exactly where we need it in order to increase that EI value. However, possibly the most manufacturable or maybe the more reasonable solution lives on this other side of the spectrum. It might be a little bit heavier, but that stiffness is a little more evenly distributed throughout the cut. And that's what we're actually going to implement here. So I will apply this and close. And now all we need to do is we need to update the analysis properties of those panels and beams in order to actually implement that section stiffness. So for example, if I open up, I have analysis properties set up for this. So if I open up my CAPS section cut stiffness analysis property, you can see I'm running all of the same things, still local buckling, crippling, and strength, but now I'm telling it to look for stiffness as well. So I will implement that on my beams. And then I will implement the solid laminate version of this on my internal substructure. And then I have a sandwich version for my skins. I could resize the whole model. It's obviously pretty quick, but I could also just swipe this selection of zones and go ahead and rerun. Now let's view some results here. You notice that we're still seeing positive margin, but let's look at our controlling criterion. So now you can see that my beams here, which are colored orange, are actually being sized according to, or actually being sized by that stiffness criteria. So it's the beams that are inheriting those extra stiffness requirements in order to meet that section target. If I open my section cut back up, you can see that I'm just over my target of 9, and I'm right here floating at 9.04, 9.05. So that's a pretty useful tool, again, in terms of communicating with other groups in your team, as well as even just verifying your model and sizing for particular properties. At this particular point, a seasoned stress engineer especially might be thinking, you know, we've made a lot of changes to the cross-section. We've made a lot of changes to the stiffness. I wonder if my loads are still accurate. I probably want to reiterate or rerun my FEM to make sure that my loads that I'm sizing to actually correspond to the type of design that I'm using. So I could use HyperX to just pump out an exported FEM with those updated properties containing these sizing results, or I can use an inbuilt tool that we have that'll do that for me. So on the Run tab here, we have a tool called HyperFEA. And as a user, all I have to do is select the number of iterations and hit go. And to give you an idea of what's going on here, it'll actually size your structure, and then this tool is connected to Nastran. It's connected to my Nastran executable. So it'll actually automatically run that updated FEM through my Nastran executable. Let me show you what I mean here. So we just ran a sizing. So I'll go ahead and start with FEA. So it created an iteration FEM. This iteration FEM has all of my updated property cards, which correspond to my sizing results. And now it's actually running that iteration FEM through Nastran. And we'll give it just a second here to actually solve. And once it's finished solving, it's actually going to automatically import all of those updated loads, which is what it's doing right now. So you see it imported all of my FEA element forces and displacements, and now it's rerunning our sizing. It's actually rerunning HyperX corresponding to those new loads. And this is something that you can do manually, but I could also have gotten up and gotten a coffee at this point, or something like that. Very convenient tool. Another way that we like to use this, and I actually have a pretty good slide to show this here, is we like to use this tool to apply FEA constraints. So say, for example, you have an eigenvalue buckling requirement of 1.0. That's the minimum eigenvalue that you want to see. And you want to size the ribs and the spars of your structure such that you meet that requirement. So you can use HyperFEA to implement that kind of stiffness target. So you see that for each iteration, HyperX knows where to put stiffness to kind of whack-a-mole these smaller modes out until you end up with this smoother case here with an eigenvalue over your target. Now with that, I think we're all finished up here. Yep. So I ran my 2 iterations. My structure has a weight of about 151 in both cases, so I can pretty readily assume that my loads are converged. At this point, I'm feeling pretty happy with my design. I know my loads are converged. I know that I'm in a good spot, and I'm ready to start thinking about producibility. I'm ready to start implementing manufacturing requirements. Now, for the remainder of this demo, I'm just going to focus on the upper skin here. So I'll say show only. And to give you an idea of the fidelity of design results that we have right now, let me show you here. So if I right click and show design result, you can see that for each one of these zones, I have an optimum design. So that optimum design contains a ply count, a core height, and a ply count. And for each ply count, I know the percentage of what plies the percentage of plies that should make up that ply count, but I don't have a discrete stacking sequence. I can't send this to the manufacturing team and say, hey, make this as it currently stands. So I need to translate these sort of effective type designs into something discretely defined. And in HyperX, we recommend doing that through what is called a laminate family. So to show you this, I will implement this from my design property. So again, we want something discretely defined. So that means we want to toggle over to actually our detailed sizing mode. And we're going to run a tool called set variables. And what it's going to do is it's going to take the optimum designs for all of those zones and generate a laminate family for each face sheet, as well as optimum core heights for each core in those zones. So what do I mean by laminate family? Let me open this guy up here. This is a laminate family, again, automatically generated based on our optimum sizing results. So each row represents a ply, and each column, starting at column G, represents a laminate or a discretely defined layup. And these are all options for sizing for each of these zones. And all of these laminates are related to one another by this column F, which is the main stacking sequence. The idea here being that if one zone picks column G and one zone picks column H, you'll be more readily able to make a more sequenced design or a more compatible global structure design out of those two solutions if you're using laminate families. Okay, so now that we've done that, we're actually ready to already go ahead and resize. So let me close my design property here. I'll select my structure and I'll hit run, continue. Okay. Now we took a little bit of a weight hit here just to make our structure a little more manufacturable. That's okay. That's something that we know needs to happen. And we'll open up our results. So first, let's check our margins. You can see we're still all positive. And if I show my design results for one of these panels, you can see that I have ply counts and now they're actually discretely defined. So this is the actual laminate that that zone needs for the top face, for example. Another thing that we might want to look at this point in terms of producibility is the core height. So let's go to our sizing results, go to honeycomb core thickness. So what we're seeing here is a pretty wide variance of core height here. It's not going to be the most producible or the most optimum manufacturable solution if we actually want to machine every single one of these core heights in here. So maybe what we might want to do is we might want to implement some sort of taper, have the maximum core height towards the root where we're seeing the most load, and let it taper off towards the end where we're seeing that it can be a little shorter. So in order to implement that, we have a couple of interesting tools. So what I can do is I can maybe select this first collection of zones, and I'll say dimension overrides table. And in this table, each row represents one of the zones that I have selected, and each column represents a variable that I can overwrite. So let me clear my min and max column here. And what I want to do is I want to apply the maximum core height of that area to all of my zones that I have selected. So it works like Excel. I can actually say equals max of my results column. And I can copy and paste that to the rest of my values. So I'll apply this, close. And now if I rerun that section, you can see I've forced that maximum of 1/2 inch core height to all of those zones. So I'll go ahead and do that down the rest of the wing. So let's say in this case, we want to implement the maximum in this middle section. Close. And then we'll do that one more time for this section at the tip. Now we will rerun this latter portion of our wing. Continue. Okay, so now we've implemented a nice smooth taper of core height down our wing. Again, We've induced a little bit of weight here, maybe about 1.5 pounds or 2 pounds were added. But again, that's kind of the cost benefit ratio of introducing more producible designs into the structure. The last thing that we might want to see in terms of producible designs or understanding where we are in terms of the producibility of our design is we might want to understand here, let me show what I mean. We might want to understand what the global layup solution in terms of the entire skin looks like, rather than just seeing the ply count in terms of each zone. So in order to do that, what we would do is we would actually sequence the laminates of these zones together to form a global ply layup schedule. And we have a tool in HyperX to do that. So I'll go ahead and implement that now. I'll select my structure and I'll hide my legend here. And from the composites tab, I'll say sequencing, and we'll start with the top face. So already automatically you can see in the table below here, each row represents a ply and each column represents one of my zones. So already my zone by zone laminate solutions have been sequenced into this global ply layup schedule. And I can actually export this to Excel, and we can use familiar formats like CATIA or FiberSim or something like that. So I will apply this, and I'll do the same for the bottom of my sandwich. Click Apply. And now if we look in our structures tree, you can see that under my upper skin assembly, I also have top face, core, and bottom face entities. So if I turn on my ply display here, and I'll hide my sandwiches so you can see a little bit better. So now you can see the actual global ply layup schedule of my wing. So my OML is actually my tool side, but if I flip over, orient myself here, now you can see the actual buildup of where plies are going to need to be laid down in order to actually manufacture this wing. And I can also do cool things like, for example, if I wanted to actually see how this might be laid up, I can turn these plies on and off to get a sense of what the manufacturing process might look like. So the last thing that I mentioned earlier in terms of manufacturability, or in terms of driving to a more serious design, is joints. So at this point, we might want to start thinking about how this upper skin is going to connect to the substructure underneath. So let me turn off my ply display and we'll kind of switch gears a little bit here. Turn my sandwiches back on. And now you're probably looking at this and thinking, you know, I don't have C bushes modeled in. I don't have spring elements or connector elements here. This mesh is pretty coarse. I didn't implement anything to tell the FEM that I had joints. But in HyperX, that's actually no problem because I can create an entity called an edge joint. So if I go back to my structures tree and say create edge joint, and let's say I want to create a joint along this particular edge of my wing to signify how the upper skin will connect to this spar beneath it. We'll say create. I'll color by joint to make this a little easier to see. And I'm going to change my selection mode to joint. There we go. So now these joint entities, which exist at the boundary between each of our zones, they act like panels, they act like beams. So all I need to do is I need to give them a design property, a load property, and an analysis property. So let's say for this case, we know we want to fasten our upper skin to the substructure below it. So I actually have a fasten joint design property already created. So let's say we want to model this edge as a single shear bolted joint. In doing so, we open ourselves up to all of the design variables that you're seeing here. So for example, we're able to select the optimum laminates for each of the sheet materials that we'll be bolting together. So if I open this, you can see that this is actually a set of discretely defined laminates that we're selecting between. Think of this as maybe determining the thickness of the edge bands that you might need beneath each fastener. We're also going to give it a set of fasteners to iterate through. So we have a selection of fasteners, all of these Hi-Loc 10 here of varying diameters that we gave it to try. And a few other things, we're going to let it size the spacing between those fasteners at each edge, as well as the number of rows along that joint. Now, joint optimization works a little bit differently than traditional zone optimization. When you're working in the acreage, you're very, very weight critical, very, very weight driven. And you're weight driven here as well, but it's a little bit of a secondary process. Maybe in this case, we want to prioritize something else. So if I toggle over to my advanced button here, I'm actually able to determine what I want HyperX to prioritize while it's sizing. So for example, here I have it set up to say, if my design fails, first change the spacing, which I have selected at sequence 1 here. If that still doesn't work, then change the fastener type. And if that still doesn't work, then change my number of rows. So now HyperX has an order or a priority that it will use to find the optimum design that I've kind of constrained to make sure it fits within my producibility requirements. So let's go ahead and apply that to our edge joints. Just like with panels, I'll drag and drop. I'll do the same with our peak load property. And then I actually have an analysis property already set up. So for our fastened joints, we're going to be running failure in the fastener. So that's things like fastener tension, fastener bending, nut thread shear, things like that. And then we're also going to be running fastener sheet strength, which is something like bearing bypass, for example, for composites. So I'll drag and drop that onto my joints. Now I'm ready to size. I'll go ahead and run and let HyperX tell me the optimum joint at each location. So now I can open up my legend and I can view my results just like everything else. So let's first go to analysis results and I'll plot by joint so it's easier to see here. So first you're seeing the minimum margin of safety of each joint, a little bit lower margins as we get towards the root of the wing where there's more load, which makes sense. We can check the controlling design load case. Maybe we're interested in the controlling criterion. In this case, we're controlled by that composite bearing, which is something we would expect in a joint like this. And we can also look at our sizing results. So if I want to see, maybe for example, the materials that were selected. So for sheet 1, we need to be a little bit thicker towards the root of the wing, but we're able to thin out to 20 plies as we get further out away from that heavily loaded area. We can also check our fastener selection. So you can see we're able to maintain the same fastener all along the edge of the joint, which is good. And then the last two things that we were sizing for were our number of fastener rows. Again, a good sign. We were able to keep one fastener row throughout the entire joint. And now the spacing in between. So we're seeing that our fasteners need to be a little closer together towards the root of the wing where there's more load, but we're able to actually space them out pretty far as we get away from that highly loaded area. And again, you can use these results to supplement your reports, to maybe plan your next model where your C-bushes should be located, anything like that. So at this point, let's say we're about finished designing and sizing here in HyperX, and now I need to communicate these results to my manager, or I need to generate some sort of report for all of this work that I've done. So to save us a little bit of time here, just for the sake of this webinar, I actually already printed a stress report for us. But you can see if I go to the results tab of the ribbon, We have several different options, everything from Word format to Excel format and everything that you might need in order to just kind of dump all of this data into a format that you can use. So in terms of our Word formatted report, we actually print out several pages of data here. So you can see, for example, the overall summary of your last run. You can have a table that summarizes the results of each one of your zones. So for each zone, we have an area, a unit weight, a weight, the lowest margin of safety, the controlling failure that caused that lowest margin, things like that. We have different margin of safety tables. So for example, the lowest margin for each load case, the lowest margin for each analysis, and the lowest margin for each zone. And then my personal favorite part as an engineer is we actually spit out the calculations for failure analyses. So if I go, for example, to one of these sections here, maybe we'll say shear strength. So we actually spit out an echo of everything that's in our help system for each one of the methods that was run. So for example, we're looking at panel shear strength here. We spit out a summary of an approach. This was completely automated. I didn't type this up beforehand. And we actually provide you every single one of the equations, curves, and corresponding data from HyperX in order to justify, verify, back calculate, if you would like, this controlling margin for that failure criteria. So as an engineer writing reports, even just writing out these equations for me saves me a ton of time. And we'll even also spit out the references here for each one of these methods. Okay, so I hope by the end of this now, you're able to really pick up on that center your design theme. So throughout this example, you've seen me use HyperX to reduce the weight of my wing. So I found the lightest weight laminates, and I was able to use both rapid and detailed sizing to explore all of the different designs that I might want to see. I was able to shorten my schedule by quickly attaining a passing design and seamlessly going back and forth between those design considerations and those producibility considerations. Also, in terms of producibility, I was able to automatically generate an optimum laminate family in order to attain compatible zone designs and then sequence those designs into something that would be manufacturable. I was able to also generate a manufacturable fastener pattern right there on my wing. And in terms of certification, obviously this level fidelity model is maybe a little early in terms of actually certifying your aircraft, but I hope you were able to see that we were from the get-go designing with respect to hundreds of aerospace analysis methods, and we were providing you results visibility the entire time. And again, that auto-generated stress report is pretty invaluable when you're generating those certification reports. So on behalf of Collier Aerospace, I'd like to thank everybody for joining us. Please stay in touch, go visit our website and follow us on social media. If you have any direct questions, please email us at info@collierAerospace.com. And if there's a little bit of time here, I think we have a little bit of time for a couple of questions if my colleagues want to kind of shout them out to me.
Hey, Charlie, we have a question here about joints. Whether for bonded joints, for adhesive joints, if it considers delamination in the composite adherent.
Right, which I can actually show. I have a design property created for a bonded joint. I guess that would be an analysis property. So when you're looking at a bonded joint, you're looking at all of those kinds of things. So yes, delamination and bonded joint adhesive strength, all of that kind of stuff. We can also look at VCCT if that's more of what's preferred.
Hey, Charlie, there were a couple of questions on section cuts as well.
Sure.
Seemed like people were pretty interested in that. The first was just asking a little bit more about, well, the specific question was, does the section cut lock onto a specific plane? I think maybe what they're getting at is how are all the different ways you could define the orientation of that section cut? So I think when you were running through it, you probably drew it by hand, I believe.
I did, yeah. So I drew it by hand over top of the section that I wanted, and then yes, it stuck to a specific plane.
So if you wanted to change that orientation, how would you go about that?
Yeah, so I can actually move this guy, so I can rotate it here in the actual window, or I could have cut it down a different plane when I drew it manually. Is that what we're getting at?
Yeah, I think that probably covers it. And so you've got and then you also have the normal vector there that you can define, and you can edit that, and then also change the position of the axes with the other vector definitions there. So there's a lot of fine tuning you could do.
Right, exactly. So these were done automatically because I drew my cut, but these are actually editable. I can go in here and change these values to whatever I need to more properly define my section.
All right, there was another one about section cuts, more of a clarification question. Does the section report generation output for only the last analysis completed?
In terms of the constraints and the properties, you mean?
Yeah, I would assume that's.
Yeah, so it will be in terms of the last analysis run. Yes, that's correct.
It's like another question just came in. Can HyperX consider the effect of statistical data, such as mean and standard deviation for composite material mechanical properties?
We can, yes. So we tried to make our material library as, I guess we'll go with customizable as possible. So for any given material allowable, we're able to implement what are called correction factors. And you can correct any of these values based on any sort of curve or maybe a table. What we have in here for the example is a table for bearing. So you can see that I'm altering my bearing allowable depending on the diameter of my fastener, for example. But this would be a place where you can implement statistical data as well.
And then did you already touch on the laminate allowable inputs that might be relevant too?
Yeah, I briefly mentioned it, but it was towards the beginning. So we also take in your laminate level allowables that'll come directly from test. So that's also kind of a statistical input as well.
Another question just came in. The imported FEM has only 2D plate elements, no 1D C-beam or C-bar elements. So maybe just touch on the different element types we support.
Yeah, so actually the FEM that came in does have 1D beam elements. So that's these little beam areas here. Let me color. That's these beam areas defining the boundary between each panel. So we do actually have P-bar cards here. We do not support C-beams. And then, yeah, each of the panels is made of C-quads, C-tris, the general element types that you might use if you're a Nastran user, and then the equivalent for Abacus.
All right.
A question, Charlie, about the failure criteria and whether there's a way to use custom ones.
There is a way to implement your own custom methods. So we actually support what are called analysis plugins. And that essentially would be a C++ version of your method that you've written, and we point HyperX to it and use your C++ code to do the math to actually do the margin calculation, and then we bring all of that back in and we show the data in HyperX. So yes, we can very easily implement custom methods.
Okay, and another question here, whether you can consider arbitrary ply angles, or if you can only analyze or size with 0s, 90s, and plus and minus 45s.
Yeah, so we are able to consider arbitrary ply angles, especially with our laminate families. You can change the orientation of those plies to anything that you might want. But the caveat is our native failure criteria are set to work essentially just for those more traditional ply orientations. We do have a plugin that we use to support those non-traditional laminates though.
I think that's a good tee up to the next question, which is related to considering like a last ply failure. It's, you know, basically a different composite analysis method, and whether that's something we can support.
That would be something that I think we would implement in terms of a plugin. So yes, we can support it, but I wouldn't say out of the box. Okay, so I guess we're reaching pretty close to time here. So if there are no more questions, I'll bring up our last slide here. Please be sure to visit us at collierAerospace.com, as well as keep in touch with us on social media. Thanks everyone for coming.